Bismillahirrahmanirrahim. Assalamualaikum and very good morning. Okay, let's continue on the second part of the Smith chart. Okay, the next part is to determine the input impedance from a Smith chart with the length of the transmission line is known. Alright, so this is the Smith chart. So you know the ZL, and then you need to determine the Zin. So the Z0, the characteristic impedance, by default is 50 or 75 ohm, and you know the length, the total length from the generator to the load, right? So the L in lambda. Okay, so if L is known, so and you also know the load impedance and also the Z0, the characteristic impedance, so you can calculate the Zin, or you can estimate the Zin by simply using the Smith chart. Right, so the steps are, first, as usual, you need to plot the normalized impedance. Don't forget to divide the impedance by Z0, the load impedance, and draw VSWR circle from the center of the Smith chart. So from the VSWR circle, you can get the value of VSWR, and then you can get the radius. Then from the radius, you can also determine the magnitude of your reflection coefficient, and we can get the reflection coefficient as well. And in order to get the Zin, so you need to consider the L, the transmission line length, and also you need to get the new wavelength of the input impedance. Okay, since you know the load, so you know the wavelength at this point. So to get the wavelength at the input point, so you need to refer to the sidebar towards the generator. Okay, looking towards the generator. Okay, so towards generator, so in this case you need to consider the current point. The current point is the L that you know. So the L, the value lambda, and then plus the wavelength towards the generator. Okay, so then you'll know the position of your input impedance. Okay, lastly, you'll plot the point of Zin on the Smith chart, and then you need to calculate the real input impedance value, because from the Smith chart you'll get the normalized value, so don't forget to get the real value by multiplying with the characteristic impedance. Okay, let's look at an example. Given a transmission line with ZL equal to 100 plus J100 ohm, and by default Z0 equal to 50 ohm, and you need to determine Zin towards the generator from ZL, and the length of the transmission line is 0.2 lambda. So L equal to 0.2 lambda. Right, so the first step is to get the position or plot the point of your normalized impedance. So ZL bar equal to 100 divided by 50 plus J100 divided by 50. So your ZL bar equal to 2 plus J2. Okay, so you plot the value into your Smith chart. So ZL is 2 positive J. So 2 is here. And then positive J2. Okay. So you'll get your impedance there. So the normalized impedance. Okay, so once you know the normalized impedance, then you will draw the VSWR circle. Alright, from VSWR circle, if you want to know VSWR, you can get the value from here. And then if you want to know the reflection coefficient, you can get the radius. Okay, and then use the same radius and refer to the reflection coefficient scale, and then it's the Smith chart. Alright, and then from there you can get the magnitude of your reflection coefficient, and also you can get the angle of your reflection coefficient. But in this case, we are going to look at the Z-in. Okay, so once you know the when you have drawn the SWR circle, then you'll draw another lines from the center of the Smith chart crossing the point of your impedance. Okay, so from here you look at the current position. Okay, the current position is here. So the current position is, you read through the wavelength, the outer part of the scale or the axis, the wavelength. So you'll get 0.2, here is 0.208, 0.208 wavelength. This is the current position. Okay, and then to know the position of your Z-in, so you need to add the L. So the current position plus the L, then you'll get your Z-in position. So in this case, 0.208 plus the L is 0.2. So you get 0.408 lambda. So you need to look at the chart and draw a line of 0.408 lambda. Okay, this is from the value of 208, and then draw a line crossing at 0.408. Okay, 0.4, 0.41, so 0.408 is here. Okay, so then you'll plot the point of the line that crossing with the SWR circle. So this represents your Z-in bar point. Okay, so then you'll estimate the value of your Z-in. So Z-in value, it's somewhere here, 0.3. And how about the imaginary? It's 0.6. Okay, so your Z-in in this case equal to 0.324, and then minus J, because it's at the bottom, at the bottom half of the Smith chart, 0.6. Alright, so don't forget this is your normalized Z-in. So normalized Z-in equal to 0.34 minus J 0.6. So to get your real Z-in, you need to multiply with Z0. Z0 multiply with 0.34 minus J 0.6. So your Z0 equal to 50. So you'll get your final or real Z in value. Okay, let's have another example. In this case, you need to determine the ZL. If you have a transmission line, this is generator, the transmission line, and ZL. So given the length is 0.2 lambda, and ZL you are yet to know, Z0 given as 50 ohm, and then Zin in this case is known. So given Zin equal to 100 minus J 100 ohm. Okay, so as usual, the first step, you need to normalize the input impedance in this case. So Zin bar equal to Zn divided by Z0. So in this case, it's 100 divided by 50 minus J 100 divided by 50. So you'll get your normalized Zin equal to 2 minus J2. So then you need to plot the Zin position. So 2 minus J2, so your 2 is here, minus is down there, and J2 is 2.0, is there. So that will be your Zin. Okay, next you need to draw the SWR circle. Okay, so once you have the SWR circle, then you can project from the center of the Smith chart crossing at your Zin, then you'll get your current position. So at this point, so you're now from here, at this point it is 0.2. okay, when you are now, the Zin, so you want to find the ZL, so you are looking at Zin towards the load, right? So from the Smith chart, you need to refer to wavelength towards the load. So it's not on the same axis as towards generator. So towards generator is pointing clockwise, while towards the load pointing the arrow pointing downward or anti-clockwise, and you need to read through the middle axis. Okay, so it's somewhere here, 0.2, 0.21, so some 0.208. That's the current position. So the total length of the transmission line is 0.2. So the new position of the ZL will be, ZL bar will be at 0.208 lambda, the current position of your Zin, plus the total length of the transmission line, 0.2 lambda, so 0.408 lambda. Okay, so you refer to the Smith chart, look at the second axis towards the load, so anti-clockwise in this case, so 0.4, 0.41, so 0.408 is somewhere here. Okay, so then draw a line crossing from the center, crossing the SWR circle, right? So then you'll get your Z load, the normalized Z load, and then read through the value of your normalized Z load. So in this case, from the graph, your normalized Z load equal to this line, it's 0.3, and then it's on top, so plus j, it's here 0.6. Okay, so this is normalized ZL. So to get the real value of your ZL equal to Z0 multiply with normalized ZL equal to 50 multiplied by 0.3 plus J06. Then you'll get your final or real ZL values. Okay, let's refer to the earlier example. So in previous example, the length of the transmission line is 0.2. So we in this case determine ZL, so we know Zin. So to get the ZL position, so the current position of Zin 0.208, and then we plus the L, then we get the position of your Zin. So in this case the L equal to 0.2 lambda. So what happened in a new case 2, if the L equal to maybe 0.3 lambda, so your ZL position will be the current 0.208, the current position of Zin lambda plus the L 0.3 lambda is equal to 0.508 lambda. Okay, if you look at the chart, this Smith chart, and this is to determine L is towards the load facing anti-clockwise. So if you refer to the scale, you'll see that the maximum is only 0.49, meaning here is 0.5 lambda. The maximum length is 0.5 lambda, but now how to get 0.508? So from this position, plus 0.3 plus 0.3 lambda, so up to this point you get 0.5. Okay, so the remaining is 0.508 minus 0.5 lambda. So you need to extend the line for more than 0.008 lambda further. Okay, so from here plus another 0.008, so 0.067, 0.008, and towards the load, so this middle line 0.008 here. Okay, so you draw the line, so you'll get your new ZL bar at this point. Okay, so you need to alert with the total length, and if you have more than 0.5, so you need to extend the line up to the remaining position. Okay, next let's look at the admittance. So why the admittance is basically the inverse of your impedance. So from the Smith chart, you can easily get the admittance value if you inverse the position of your impedance, the normalized impedance. So let's use the earlier example. So you have point A, if you have the ZL equal to 50 plus J50 ohm, so normalize ZL for A equal to 1 plus J1. So 1 here plus J1. So the point A is there. So the admittance will be, so you draw the SWR line as usual. So center at the center of the Smith chart. Okay, and then you draw the line from the center crossing to your normalized impedance. So this is your ZL. So in the translation or in the opposite, you'll get your admittance. So Y of A. Okay, so from the admittance, then as usual, you can get the value. What's the value of it, and also the imaginary part of it. Okay, and then same goes to the case B. If you have the real impedance, load impedance equal to 300 minus G25, so get the ZL. So you need to determine what is your YL of point B. So ZL at point B, based on the normalized impedance, 6 minus G05. So 6 is here, and then 0.5 is there. It's crossing there. Okay, so this is your point B. Okay, so ZL of point B. So the admittance will be on the opposites. Okay, so you draw the line from the center, crossing the impedance point, and then extend the lines to the other end. So you will get your admittance here. Okay, so YL at point B. Okay, so that's basically the admittance. Okay, so in summary, let's look at the points of the impedance and also the admittance. So if you have Z, the impedance, normalized impedance 1 plus G naught, so 1 will be there. So since G naught position is on the horizontal length where it is in match position, so if 1 plus G1 ZB is there, and then ZC, if the real value is infinity, so it is an open circuit, ZC. So the value at this point is open circuit where the Z load is infinity. And if you have short circuit, the load impedance is 0. And if you have the negative or imaginary part or reactance, ZE, and the admittance will be in the opposite or in the translation of the impedance. Okay, for match position, the admittance and impedance will be at the same point and it is matched. Okay, for ZB, it's here, so then the admittance will be in the opposite. Okay, if you draw a line crossing the center. Okay, for open circuit, it will be in translation or in opposite. So if it is open circuit, Z naught will be the load impedance is infinity, but the admittance will be 0. And for short circuit, vice versa, or in translation of ZD. Okay, and the other part is YE, it is in the opposite of ZE. Okay. Okay, let's look at an example. So before that, please make sure you have your Smith chart in hand with the protractor, compass, ruler, and etc. Right, given a transmission line with length of lambda over 8, so the L is lambda over 8 and 50 ohm characteristic impedance, so Z0 is terminated by a 100 ohm load impedance, so ZL. Referring to this transmission line, determine the followings. So you have a transmission line, the generator. Okay, I will recommend you to draw or to sketch the basic transmission line and include all the parameters or the values that you have. So you have your ZL equal to 100 ohm, and then the transmission line L equal to lambda over 8, and then you have your Z0 equal to 50, and as usual you have your Zin, and also you have the source or generator. Right, the question asks you to determine the input impedance Zin and VSWR. And then find the input impedance when the load is changed to short circuit and open circuit, and also with the variations on the length of the transmission line. Okay, let's use Smith chart and compare with the calculation that you have performed earlier from the earlier example. So from the earlier calculation, you will get the input impedance equal to 40 minus J30 and the VSWR equal to 2. Okay, however, this you can look at the equation if you can remember, or if the equation is provided, then you can use the equation to calculate. Or else, if the question states clearly by using a Smith chart, determine the followings, meaning that you still need to perform the solution by using the Smith chart, although you know or you have the equation in hand. Right, please read through the question carefully, so in order to get full marks or to get higher marks for your steps. Right, so from the given question just now, you have a transmission line, okay, with terminated by 100 ohm ZL, and you have the characteristic impedance equal to 50 ohm and the length equal to lambda over 8. Alright, so Zin is not given, so you need to determine the Zin. Okay, from the calculation, if you are asked to calculate, then you can use the equation and you will get the Zin equal to 40 minus J30. Okay, but if the question asks you specifically to solve the question by using a Smith chart, then perform the first step. As usual, you need to find the normalized impedance, load impedance equal to the value 100 divided by the characteristic impedance Z0, so 100 divided by 50, you get 2. So then plot the ZL on the chart. So your ZL equal to 2, and there's no imaginary part, so 0, so it's 2. Here is your ZL, normalize ZL, and then as usual draw the SWR circle. Okay, so then measure or read through the SWR value. If the value is not clear, then you can use the same length, the same radius, and use the scale underneath the Smith chart. Okay, so bring down the same R to the SWR scale, so it is equal to 2, so it's the same reading as on top. Okay, and then if the question asks you on the reflection coefficient, then bring down the same radius down there, so you'll get the reflection coefficient. Okay, so if you and then okay, so you get the SWR equal to 2, so it's the same as the calculated value. Right, next is to find a Z-in. So as usual, you need to have the line to indicate the current position. All right, so the lines here, and so to determine Z-in from the current position here, so you'll see towards generator. So look at the axis towards the generator here, so you'll be looking in clockwise motion or clockwise view. So the current reading on the outer axis is 0.25, this one. All right, so 0.25 lambda, and the length is lambda over 8. Okay, so lambda over 8 is equal to 0.125 plus lambda over 8, so you'll get 0.375. Okay, so find 0.375 from this from the outer or towards generator scale. 0.363738, so 375 somewhere here. Okay, so draw the lines crossing from the center. Okay, and then look at the cross section in between the lines and also the SWR circle. So you'll get your Z-in there. Okay, and then read through the real and imaginary part of the Z-in. So it lies in there. So your Z-in, normalized Z-in equal to 0.8, and it is at the bottom minus J. So look at the this way. So it's 0.65. Okay, so your Z-in real value equal to 0.8 minus J 0.65 multiply with your Z0, it is 50. So you'll get 40 minus J 32. Okay, so there's a slight difference between the calculated and also the view. Okay, maybe due to the position of the plot on the scale. All right, and it's just slightly different in the imaginary part. Okay, but the magnitude is the same. Okay, next the question asks you to determine the input impedance, again the Z-in, if now the load is changed to short circuit and open circuit. Okay, earlier the load is 100 ohms, so now you have two conditions. The condition A is short circuit, so your ZL equal to 0. Okay, and the length, the default length equal lambda over 8, and the characteristic impedance is the same. Right, so determine the input impedance if you have the short circuit, so ZL equal to 0. So if you calculate the normalized impedance, it is 0. So plot ZL. So here is your, if you remember, here will be your open circuit, here will be the short circuit. Okay, for the real part. Okay, and then get, so at this point now it is the load impedance, so get the wavelength, the current position. So to determine the Z-in, so you'll be looking towards the generator, so it will be in this way. So the value now is 0, So if it is lambda over 8, it is equal to 0 plus lambda over 8, 125. So you'll get there 0.25. So the circle where the load lies on is around there. So it's crossing at this point. So there will be your Z in. Okay, so this is your Z in for L equal to lambda over 8. Okay, so you can read through the value. So at this point, the magnitude is 0, the real part is 0, and then the imaginary part, as usual, you can read through the value. Is equal to 1 here. Okay, so in this case, the Z in equal to 0 plus J1. So to get the real value, multiply with Z0. So Z in equal to 0 plus J multiply with characteristic impedance 50. Okay, so it's the same as the calculated one. Alright, so in terms of the reflection coefficient of the input point, then you measure its length and then bring down to the scale and look at the value of the reflection coefficient, and don't forget to measure the phase for or the imaginary part for the input impedance. So refer to the scale. So reflection coefficient in degree, okay, is the second axis. So somewhere here is 90 degree. Okay, so you get 90 degree. Right, same goes to when you change the L equal to lambda over 4. Okay, lambda over 4 equal to 0.25, so 0 plus 0.25, so you get 0.25. So your Z in at lambda over 4 equal to this point. Here is Z in at lambda over 4. So again, you can read through the value and also the imaginary part. And same goes to when it is lambda over 2. So 0 plus lambda over 2 is 0.5. So Z in when lambda over 2 equal to the same point as the Z. Okay, the load position. Okay, and repeat again for the open circuit. So the open circuit is supposed to be somewhere there. So in this case, the Z load equal to infinity. Okay, so the open circuit position is at this point. And to determine the Z in, still you need to look at towards generator. So if it is lambda over 8, so at this point, towards generator, so it's 0.25 plus lambda over 8, then you get your 0.25 plus lambda over 8. So I can't see the scale clearly, but it's 0.375. Okay, so repeat again for lambda over 4 and lambda over 2. Okay, so if you look at this is for open circuit. So the point is there. Okay, so you get your the magnitude is still 0, and then the is minus J1, so multiply with the characteristic impedance, so you get the real Z in equal to minus J50. Okay, so repeat for lambda over 4 and lambda over 2. Okay, let's look at another example. Okay, load impedance of 40 J 70 ohm is terminating a 100 ohm line that has a length of 0.3. So a load impedance, so ZL, terminating a 100 ohm line, so characteristic impedance in this case is 100 ohm, and the L given is 0.3 lambda. So again, I recommend you to sketch this equivalent circuit or the transmission line and put the values in, and this may be considered as part of your steps in solving a problems. Right, find the reflection coefficient. So this is equal to the magnitude of reflection coefficient and theta at the input line. Okay, reflection coefficient in the input impedance, the Z in, and then SWR, and also return loss using Smith chart. Okay, using Smith chart. Okay, so again, basic step, find the normalized ZL. So you have 40 plus J70 divided by Z0. So you'll get your, so Z0 in this case is 100 ohm. Okay, please be careful. Z0 equal to 100 ohm. So you get your impedance, normalized impedance 0.4 plus J 0.7. So now you find the plot or plot the ZL on a Smith chart. 0.4 3 4. Okay, this line, and also positive, so on top 0.7 is there. Okay, it should be there. So your ZL. Okay, then once you have that, you can draw your circle, SWR circle as usual, and then to get the SWR value, so you can just get the radius. Okay, you can read through the SWR equal to 4, or if you cannot see the scale, then you can bring down the value underneath towards the SWR scale, so you get the value. It is not exactly at 4, it is at the 3.8, okay, somewhere here. So your SWR equal to 3.8, and then what else? Return loss using Smith chart. Then you can bring down the same scale to get the return loss using the same line. So it's around 4 point something, 4.8. The return loss, or S11, it's 3.8. Sorry, 4.8. And it is in dB. And then the what else? The reflection coefficient at the input. Okay, the question asks about at the input point, not at the load point. Right, so now you can find the Z in. So look at, as usual, draw the lines so you can see the current position. So to determine the Z in, so you need to look towards the generator. So towards generator, looking this way, and the outer scale. So the current position is there, 0.106. Okay, 0.106 lambda, and then you need to add up the length, 0.3 lambda, so you get 0.406 lambda. Okay, so find 0.406 lambda. So 0.4, 0.41, so here, and then you draw the cross section between the line and also the SWR line, so you get there. This is your Z-in. Okay, so find the reflection and also the input impedance. Okay, so get the value of your Z-in somewhere here, so around 0.35 your Z-in, normalize 0.35 minus and J 0.6, J 0.6, so your real Z-in value will be multiplied by 100 ohm, your Z0 multiplied by 0.35 minus J 0.6. Okay, so you'll get your Z-in value, and then the reflection coefficient at the input line. So reflection coefficient, use the radius, so you'll get the magnitude of reflection coefficient equal to the same value as your so you need to refer to the scale again. So the reflection coefficient will be 0.575, and then the angle of your, okay, look at the reflection coefficient, the second one here. Okay, so negative the second, so negative 1 something, 113 maybe. Okay, so this is the this is the reflection coefficient. Okay, the magnitude is 0.575. Okay, so you have determined this, and then you have the input impedance, yes, and then you have the SWR, and also you already have your return loss. Okay, so there are more examples included towards the end of the video, so you can just read, you can try out all examples, and the solutions are provided, so you need to try out the calculation and also the by using the Smith chart to prove. Okay, and in this slide, okay, to calculate lambda, it's C over F. You know that lambda not equal to C over F naught, but if you are having a dielectric material separating the transmission line or field within the transmission line, so you need to consider the permittivity of the transmission line. So the lambda now become lambda effective, so C over, considering the dielectric material permittivity and also the F, the frequency of operation. Okay, so with that, thank you.